Okay, good. All right, so I know it's day 2, but we're still on some of the material from day 1, but it's okay because it looks like I go off tangent sometimes, but I'm talking about material that sometimes we're ahead of, so we kind of mix it up throughout the whole process. So we got through a big chunk of stuff yesterday. So 193 in the book is where we need to be, because I'm going to start talking about these ATA standards again and try to make sure that these are clear to everybody, because this will be the stuff that makes its way into every tool that you use. And if the tools don't have these controls, then you're using the wrong tools. So InCase is not a data recovery tool, even though they like to believe they are. FTK is not a data recovery tool. You can use it to obviously get to file systems and get to certain things, but they are not doing what I think is the hard part, which is you have to get every single sector copied somehow. And so many of these other tools, and padding with zeros is not acceptable to me if you can avoid it. So in my opinion, all of those tools needed to, or should have at some point in time, looked at other ways to do something to get more advanced. So my goal is always going to be as respectful to the drive as possible, get all of the sectors, get all of the hardware working, get everything I can from it. And again, some of you dealing with encryption already know you've got to get it running, or you can't get past the encryption in many cases. You can't get some of the items working in MFT entries and tables if you don't have the sectors, because they're gone, and catalog IDs and things like that. So I'm going to focus on the hardware side of the imaging that you cannot really do easily with software. The closest thing to software that you would have been able to do is DD Rescue. So on Linux, you could use DD Rescue for free, basically to do some of the tricks that we would do with hardware. But after 2007, 8-ish, when they started adding these other features into the tools now that we have, such as turning off heads, repowering the drive on the fly, things like that, those are things DD Rescue cannot do currently. I don't think it'd be terribly difficult for someone to write a USB adapter tool that could turn off and on a drive and reset the drive from DD Rescue, because in software you can send the signal to a relay, turn off the drive, turn the drive back on. So it would be possible for somebody to make like a $25 cable that would add to DD Rescue doing those kind of things. But as many times as I've said it, nobody else has ever done it. There's no money in it, let's put it that way. There's not going to be any money in it. So again, at least from this standpoint, there's going to be a lot of features inside the Deepsbar, the Atola, PC3000 that things can happen. And this will apply to all of those things. So I'm going to try to give you the basis of that. So the T13 Committee is the committee that decides all of the commands. And that is the committee that everybody needs to talk to in order to make their drives work. So they are the ones who started. When there was no committee, there was nothing back in the early days, the late 80s, early 90s. There was nobody guarding standards or making standards. Things didn't work together well. There was a whole mess of things that happened, and you had to be an expert to keep your system running, just to keep it running back then. So when they created the committee, they started adding things, and Microsoft was a big part of the committee. There's all of the vendors, Intel, things like that. Everybody is in that committee that has decided what those commands are. Then they transitioned to SATA, and they basically started over again. They took the old commands, they transferred them to a new basis for SATA, and continued on. So then SATA has its own set of those types of things. So when we're talking about here, we're talking about IDE drives, just the beginning of IDE drives as far as what we're concerned with, which would have been late 80s. And then really till we get to about here, this is when we start having Windows 95. Windows 95 is kind of our first version of things that happened that now software and hardware are affected by everything together. The very first release of Windows 95 didn't have anything else added to it that would affect hardware until the second version, which was called OSR2. And OSR2 was only distributed to custom builders. It wasn't distributed, I don't know if any of you ever saw that CompUSA party that everybody went to in Windows 95. I'm not kidding, it really happened. When Windows 95 was released, it was a midnight party at CompUSA. Everybody went there and got their release of Windows 95. And they had a huge party, and everybody was celebrating, and nobody was installing operating systems. But it was a geek fest. Maybe one of the first ones. But following that, from that standpoint, the big deal was that OSR2 added 32-bit. So you could literally now use UDMA and get to 32-bit because the very first release, while it added long file names, did not add 32-bit. It was still 16-bit based, and then went to 32-bit OSR2, and that's when things became more usable, more Mac-like, if you want to kind of put it that way. The Mac was kind of far ahead in the way some of the other stuff happened because they always used the SCSI protocol, so they didn't have some of the things that held us back in the PC world, per se. But of course, at that point in time, the Mac, there was no terminal, there's no power user, there's no nothing. If you didn't use a mouse and click a button, there was nothing you could do. There was no control mechanism there. So a lot of people kind of thought it more of a toy, and that's why it worked for graphics and word processing, and that was about the extent of what anybody was doing on it. It wasn't a powerhouse from that standpoint. So on the PC world, we start building forward. ATA Spec 1 adds so Pio mode is called Programmed Input Output Mode. That is the way all hard drives talked to everything prior to OSR2. Prior to Windows 95 OSR2 coming out, you only talked to your drive through Pio mode, which meant that it was a slow transaction. Every single thing had to go across the CPU, basically. It had to be involved in every transaction. So the CPU had to make the request and do it for you, slowed the entire system down. Then we get to DMA, which you could start doing direct memory access. You could start making requests across the bus, and the CPU is not involved in every transaction. So now handling the I/O is now a separate process from doing it directly through every single step one by one. Does that make sense to everybody? Now, we, most of the time, never use Pio mode anymore today, because as soon as you plug in a hard drive, it says, what's the highest ATA spec that I can run? And it'll tell your motherboard what it does, and then it'll automatically fall into the highest. So we'll be at UDMA 6 or something like that right away by default in all of our systems. And that's how we've gotten faster and faster over time. But Pio mode still exists. It's still available for every hard drive to communicate. You can still fall back to it. And I equated a little bit similar to when we got CD-ROMs. When CD-ROMs first came out, they were all 1x. There was no, you didn't call it 1x. That was just the speed of a CD-ROM. It was like JAWS. There's no JAWS 1. There's just JAWS 2, and same kind of thing. After the 52x comes out, every time you record a song, you record things and put it on there, you started having jitter. You remember this problem, the jitter problem with CDRs and CD-ROMs? So they tell you, in order to fix the jitter, you drop it back to 1 or 2x, and then record it that way, and then it fixes the jitter. Because whatever was going on in the transfer wasn't getting to the disk fast enough, so it caused some frames to be missed, and then all of a sudden you were having jitter. So that's specifically what's going on here with direct memory access, and going forward from here, we're able to add on to some other transfers and get it to go faster. But sometimes if we drop back to the old methods, we can get a hard drive to work, never worked under DMA. So DMA is still memory, and it still requires, when they're building a hard drive, they're trying to get a quote from somebody for whoever has the best 5-cent chip. And whatever they're going to cost to put it on that drive, it may be a cheap, crappy chip. There's been several hard drive companies that have gone kaput because they bought a crappy chip from somebody. Fujitsu is one of the big ones. Fujitsu used to make 3.5-inch drives. They were considered one of the best drive manufacturers in the world at the time. Their SCSI drives were better. Their drives were better as a whole. And so they're super rare to run into them or to find them. But one of the things that happened, this is a Fujitsu 3.5-inch drive. So Fujitsu decided to farm out a quote for manufacturers for their board. And one of the chips that they were trying to get that they were cheap on, this particular memory chip, CPU, the product people who made this used an inferior type of plastic that breaks down during the process. And so what happens is, as the drive gets colder, it stops working. So it heats up, and it works fine while it's hot and it's in use. As it gets colder, then the drive never starts again. And it's a breakdown in the plastic over time, and it's all because they used a cheap manufacturer. This put them out of business. They never made another 3.5-inch drive after this. That was it. They only made laptop drives. They never recovered from everybody's drive dying, basically. All because of chip. If you ever see one of these that you need to recover from it, here's what you do. You cover everything with aluminum foil, or you can use polymod tape, cover everything so that you've got a heat sink, basically. You leave the chip exposed. You put a drop of solder in the center of the chip. You point a heat gun at it until the solder melts. When the solder melts, it's high enough, at a high enough temperature, that the chip will work. So then rub the solder off, don't let it drip all over the board, and then just power it up. And so then it will work, and you can do a recovery from it. So if that ever happens, it'll probably be very rare that you'll see them, but if that ever happens, that's what it is. So, but those kind of things put people out of business. So I'll pass around if you guys want to see it. You guys want to see it? Yes? Do you have some of these?
I think I might.
So the ATI specs, as we continue going forward, the biggest one is we have Pio mode, and then we went to LBA 28-bit mode, and LBA 28-bit mode added a command called ignore ECC. You guys remember this from yesterday? So if you have ECC, it'll turn off the ECC, it'll get the data back, even though the request would be 0 if it was an error. Does that make sense? So I equate that to in-case FTK. All right, and then we added smart self-monitoring analysis and reporting technology in ATA 3. The problem with smart is this: it can cause your drive to die. It was added on to tell you if your drive is going to die, but it is also the cause of your drive dying. If a smart table gets corrupt, when the firmware tries to load it, it doesn't know what to do with the corruption and dies. So it actually hangs up. So one of the first things that happens for data recovery with most of the steps that we do is clear the smart table. So there's several different drives. The Toshiba is one of them, that the smart table, when it gets corrupt, the drive just dies, won't work. Seagate also has that problem. So that is 2 of the steps in some of the tools. And even though the Deepsbar is not a firmware tool, they added this extra screen, and I'm going to show you. So when you first power on a Deepsbar, and we're going to back up a little bit later, and we'll take steps to get here. This is the default first screen you'll see on the Deepsbar. It's showing you I have a drive that is connected, ready to write data to. I do not have a source drive currently. There could be a problem where the source drive isn't responding correctly because the smart table is corrupt. Okay? Depending on the drive that you have. So Deepsbar did write a command. It's a secret command you can't get to from here. Like you can't see it on a menu, because you can't get to these menus. I'm going to hit characters. You can't get to the menus across the top until you're already into the drive. So once you're into the drive, you could see the menus and you can then interact with the menus. Okay? But I'm at a selection spot because I have no source drive to connect to it. If I have a drive, and you'll see the key is F9 is the character. I haven't gone back and read Deepsbar's manual in about a year or so. Every once in a while they add the stuff that's not documented into it. I know a lot of undocumented things, so I'll tell you what they are, but they maybe have added to the books or something at some point in time. But F9 pops up vendor specific function, which is really firmware. So this is a communication with firmware. And so before I've ever even selected a drive, so you'll see that on a Toshiba, one of the items that is a normal problem is reset smart. So the smart table gets corrupt, causes Toshiba to hang up. Now there is one with Seagate too, but those are firmware patches that you've got to do more manual work than what this tool can do. So if there's nothing else involved other than sending the command, Deepsbar will add this to their list. So these are the ones they currently have. Western Digital does have this slow responding issue, and so it's sometimes if your drive is responding very slow when you're copying sectors, you run this command and then all of a sudden it picks up. It's called like a dead man search. The drive is off doing something else for cycles while it's trying to copy your data, and it's a bug, again, the Western Digital goes crazy doing something else, and it slows your process down. So there's a slow responding fix to get past some of those things. So there's a variety of different types of issues, and like I said, they may add them in newer versions, and they sometimes they even have command line when they're testing something out. So you can sometimes call them and they'll tell you when you're starting up the DDI, put a dash and put these characters, you know, like S5 is to pull for a longer period of time, things like that. So there may be some, but they don't like to use those. They only do them for like testing processes. They'll tell you later. So if you need something, you can call them and find out, but you may not know you need it. So anyway, so F9 is one that gets you to some of those firmware functions, but I'm just demonstrating that the glist, the smart table is sometimes one of the ones that causes a problem. And so smart is not useful for anything except giving you information. It does have some testing, really extensive testing processes that you can go to, and you can use tools like there's one that's called G-Smart Control. And G-Smart Control will allow you to control all the aspects of the testing process and a bunch of things that you would not normally have access to. There is quite an extensive list of things in Smart and Extended Smart that will do things that you wouldn't have imagined, but they're all turned off in the drive by default. So when the drive comes up, all the drive does is go, "Are you okay?" "Yeah, I'm okay." "All right," and then goes on. That's it. There's nothing else to it. It literally says, "Is your table okay?" "Yeah, my table okay," and that's it. There won't be another response. But there is an extensive testing thing where it could have done like your old memory test, where it checks out every buffer and make sure that your memory was fine before you actually booted your computer, that you just hit escape and you would avoid, so that your machine would boot faster, because everybody's into, I got to boot faster. So anyway, so that's something else that we're going to use or deal with. In ATA 4, we added host protected area. I've got a whole slide on that. I'm going to go to that slide in a minute. CF adapters. That's compact flash. Use compact flash at all? Compact flash is the most unusual of all the memories that it exists, because compact flash has an ATA spec. It can actually be treated as a hard drive. It does not all the other memory, every other memory, so SD cards, anything else that you want to talk to, always goes through a USB adapter of some kind. So even if you get an adapter that looks like an IDE adapter, it's not an IDE adapter. It's a USB adapter to an IDE adapter. They always have a chipset on there to control them, to convert them from one thing to another. There is no direct control of any other type of memory. Now, solid state drives are different. So, you know, when we're talking about solid state drives, they emulate ATA commands. That's what they're supposed to do. So M2s and PCI, like express cards and things like that, and then your regular SATA drives. Those things are all emulating some commands of ATA. Again, it's an emulation which isn't true. It's not real. They fake out the system into believing I'm a hard drive. And so that was a requirement by Intel in 2006. So from then on, you can't really trust their interfaces. But a CF adapter, you can use just a converter straight into, now make sure that whatever you buy isn't CF to USB, then to whatever it is that you're plugging it into. You can get a real converter which has nothing else in it. There's no other chip in the way, nothing else stopping it. It literally goes CF straight into the machine into an IDE adapter. And so that you can do a recovery directly. And when you buy a Deepsbar or PC3000, they come with them and they connect to the ribbon cable that comes off. So you'll have a ribbon cable that's connected right here on your IDE interface to talk to those devices. But it is the only memory of all of them. And so that also means you can use it to boot from. And you know, I know people think that you plug in a USB stick and you can boot from it. That was a lot of work to actually make that work. It doesn't work natively. It actually is packaging content separately, and then your EFI or your BIOS has to know about it and make it boot that way. That was not native. That is not like a CF card where you could take like an old DOS machine and you can make it work. So you can use a CF memory stick as an actual bootable device and keep track of log files and things like that, and you'll see where this might come in handy in a little bit. And then the next thing we got up to was ATA 6. Now there's there's 2,000 things inside of every one of these ATA specs. I'm just showing you the stuff that's important to us for data recovery. But when we got to ATA 6, we got to LBA 48-bit. Now, in LBA 28-bit mode, we had this ignore ECC command, and they said obsolete, we're not going to use it anymore, turn it off. So Deepsbar had to do some tricks to use LBA 48-bit mode past 137 gigs to read a drive. So, because you cannot use LBA 28-bit mode, so it's a little bit like doing forensic memory analysis. The Deepsbar, the data for the content gets dumped into memory. Then the drive reports an error and says, oh, I couldn't read this because ECC said it was bad or whatever. But it already dumped it into memory on the board of the drive. The Deepsbar reads the memory and then gives you back the content from the memory of the board. Does that make sense? But the problem is the same as you have with memory anytime. You dump stuff and then you dump stuff again, and some of the crap is still there from the previous one, so there's some overlap, and so you end up with chunks of crap. And so they try to rebuild the data doing the same process that I described yesterday, where they build an array, they look at the bits, then they try to figure something else out. It'll work, they'll try it, it won't work as well. You won't get as good a response as you get straight from the drive. It's coming from memory, and it's just chunks of crap that it's trying to figure out. But it's better than no crap. Does that make sense? So we'll get to that spot. And then we move on from there to all the other SATA items. And SATA as a whole doesn't mean a whole lot to us. The original hybrid drives were different than the current hybrid drives that we have today. And most of the time when you buy a hard drive that has spinning disk and memory, flash memory on it, that what's really happening is like 30 gigs of that is divided up into two partitions. Part of it is for your ready on cache, and the other part is for paging, basically. It's the ready boost version of what was supposed to happen in a drive. So even though it has the solid state content, it's really not being used technically by you. It's really being used by the system, by the machine. Does that make sense? The exception to that is Apple. Apple actually has So in Windows systems, when you have a mixed drive that has solid state and spinning disk, you typically do not have the usable portion of flash with LBA numbers. They're technically being used by the system and the operating system to do things to make the system run faster and to come on quicker. And all your LBA blocks are still on the platters in order. Does that make sense to everybody? That is not what Apple did. Apple said, we're going to make a fusion drive, and they are going to take the first part of the LBA numbers and renumber the solid state drive, so those are LBA numbers, and then bleed them onto the spinning disk, and then those are higher LBA numbers, and then they use a piece of software in the middle that is a controller, basically, that is core storage, and it decides what's important and what needs to go to the solid state and what needs to go to the spinning disk, and kind of still uses a defrag process to make that happen, is the best way for me to lay that out. So it's making use of a defrag process to say, these files have been opened more recently, and he uses them 100 times more than any other file. Let's move those to the solid state drive so they're more ready to be used than they are on the spinning disk. So when they die, you have to do both pieces, whereas on a normal Windows machine, I don't have to pay much attention to the flash memory at all, because all the data is still stored on the other portion of that except whatever was cached. That's still sitting in page files and other content. Does that make sense? All right, so let's talk about all these other things that we can do at this point. So this is the basic layout of all of the commands that we would have that would allow us to control, and they're all based on speed primarily. They're all, how are we going to talk to our drive in a more stable fashion in order to get something recovered. So this is the first 85% of the drives that I was telling you about yesterday morning. Seems like such a long time ago. That basically is, I don't have to necessarily open every drive to be able to discuss with this drive how to recover your data. And so Now, these also apply to the ones that we're manually fixing, because we may need to slow them down or do something because they're not responding quite right because we played with the head. We took out the head, put a new head in, we fixed the drive, and now they won't respond exactly the same way they would have as if they were made by a robot. So we may have to change things, slow things down, and make adjustments. But these will be where I'm looking for things. So programmed input-output mode, DMA modes, which amazingly a number of times just DMA by itself and turning off cache and DMA and things like that solves a lot of problems. And then switching back and forth between logical block addressing 28-bit and 48-bit with ignore ECC. Those are our major options that we have. Now I know it just, again, I'm throwing words at you, so I'm going to show you so that it applies to something. Now, ignore ECC does not work on every drive. The reason is that some commands, when they became obsolete, somebody might not have added the code in, or somebody might not have had a piece of code that was already working. So you have to test certain drives to see if it functions or not. Now, I'm using a Toshiba for this example. I already know Toshibas will not respond correctly with ignore ECC. That doesn't mean I can't show you how it works, because you will actually do it in class this week on the drives that you're going to get. Some of them will work, some of them might not. The two drives that mainly do not work most of the time with certain commands are Toshiba's and Samsung. Samsung is the shit drive of the pile of drives that are out there. That's the best way I could say it. So I apologize for the cussing on that, but that's how I feel about it. It's the worst. If you see it, Samsung, you always go, oh. Like, there's no other way around it. They don't support their commands. They didn't build tables. They didn't do a whole bunch of things. They barely got that drive working. That drive barely worked, ever worked. And so just know, if you're working with a Samsung, there's a lot of bad and there's only one good. The one good thing about Samsung drives is they're usually pretty easy to rebuild. Like the physical heads assembly, sometimes they even made like a little platform for the heads to sit on a post, and they align really easily. So it's really easy to rebuild them and get them running again. It's just very hard to read certain things from them because the commands are so poor and so poorly supported. Does that make sense? All right, so all right, when I start up a DDI, and this is what you're going to be doing today after lunch, you're going to start doing this process. You're going to be rebuilding drives, and then you're going to be taking them to the Deepsbar, and you're going to be getting it running. When I first start, and I'm going to cancel. I'm going to quit so you can see what I'm going to do to start. When the machine boots, everybody in front of them on the machine has a connector of some kind that is plugged into the motherboard. This is actually how I run them in my lab, because I can pick up motherboards and move them wherever. And so I'll have 6 or 7 running in a row, and I need something special. I'll go get a connector that I need. I'll go whatever it is. So this is technically how I'm running everything. I stopped building boxes around stuff years ago because they only get in the way. You spend a lot of time unscrewing and screwing stuff. And so I'm grabbing SCSI adapters and RAID array adapters, and I'm sticking them in machines, and I'm adding machines together and making something work. I'm fine with them being on a table. Does that make sense? If you want to build a pretty box around yours, feel free. But this is literally the best way for it to work, and I'm always just grabbing stuff in and out, and I don't need screws most of the time. So when you power on the machine, it's going to go through a boot process, and here's the thing. I have these completely loaded. Like the Deepsbar has every module on it that you can buy. So it thinks there's a network. I don't have a network set up. There's no network cables. That's a whole nother, I mean, it already takes 6 hours to set up in here. I'm not building a network too. So they're going to ask for it, and they may give you an error. They may say severe error when you first boot. And the severe error is there's no network. And then you just hit enter and you keep on going. And then you'll get to a prompt. And the prompt, you type DDI. Now, if the numlock is on your board, because I do not have a regular keyboard, I have little sub keyboards here. If the numlock is on and it's highlighted, then when you type I, it's going to be a 5. So that happens because I drag these motherboards all over the country all the time, and sometimes when I power them up, the BIOS has been cleared, so therefore it resets back the numlock all the time. You can clear it, you can turn it off in the BIOS so it can stop annoying you, or you can just hit the numlock. In the bottom left on these keyboards, the 5th key over is numlock, and you can just hit numlock and then type I, and it'll be fine. Everybody good? So just know the numlock is on a lot of these. And then I hit DDI, I hit enter, and then it starts here. And this is where everything happens from here. This is the screen you should always be on when you are rebuilding your hard drive. Because when you are trying to read your drive and you're trying to get your head assembly realigned so that you know that you're reading something, you need to be on this screen, because I will constantly refresh this to see if I can read content from the identification of the drive. And the reason is this. Where is the serial number stored on the drive? Which is where? Huh? System area. And where is the system area? On the platter. So if you read the system area, what do you know is true? What? Speak up.
You can read the drive.
You can read something. A head is working, and it read a platter. Maybe not all the heads. Maybe only one head. Maybe copy 0 wasn't working, and copy 1 was working. I don't really care. The whole point is I read something. And so I know that a head is working. Okay? So this is one of those things that happens. I see things all the time where people will be like, oh, I'm booting my computer and it said NT loader not found, so I ripped the heads out and I replaced them. Like, you're even past where the drive identifies. You're now into data and you still rip the heads out. So part of your diagnostics mode is actually knowing what is going on by seeing certain things and understanding what's happening. So there's also this concept that every time that a machine is plugged in, that if you don't see your hard drive in the BIOS, that it isn't usable, or that the drive isn't going to work on your system. And that's not true either. They have nothing to do with each other. I've literally had this conversation with IT guys all over the world. They think that if the drive is powered on afterwards, that it can't be pulled on the bus and can't come up. That's bullcrap. Even IDE drives could do it. You could even hot swap IDE drives. The problem was the power, not the connector. And we did it in forensics all the time. The original first guidance boxes, the first Tableau and those fast block boxes, those were live on the channel and they had a separate power switch. You plugged in an ID drive, you flipped on the power switch so that it wouldn't short. And then you could pull the bus again and it would come up on the chain. So you've always been able to do it for IDE drives, for SATA drives, for any kind of hard drive. You can pull the bus. Does that make sense? After the fact. It does not have to be on when the BIOS is on the machine. So now we're in a spot where basically what's going to happen is I would power on the drive. I'd be looking for some commands to happen. The very first thing I should see is it should say busy. And so you don't normally ever see busy on a machine, even if because you don't have a display, but besides that, when the machine is booting, it's going through a post process. And all of these other things on the hard drive are happening during the post process. Now you're connected directly to the drive, you can see them step by step. So I'll see busy, then what should happen is the head would seek the system area, read content from the system area. If the drive was open, you'd actually see it do that. You would see it go from the outside park or wherever it is in park, there's 4 positions for park, and then it would seek the system area. You'd actually see it do it. It'd go to a location on the drive. It'll jiggle a little bit, read content, and then it'll return to another position and then just keep gradually moving across the drive slowly. You won't even be able to tell with your eye, but 20 minutes later you'd see that the head was moved, because they do it for wear leveling, because they think the magnetism over the head sitting over the same place on a platter will cause damage if it's there for too long, so they gradually move it track by track by track by track to keep them alive. So not every drive, but most drives do. So anyway, so this is what I'm looking for. After it reads the system area, that meant that drive seeked and then it completed. So you get 2 commands. This is like a terminal on a modem, if any of you are old enough to remember a modem. So in the olden days, we used to have to connect to our bulletin boards. There was no internet. You used the modem and you transferred files, and you could actually tell, if you did it enough, you would be able to tell what your modem was doing. You could even you could turn off screens and everything, and you could walk in, you could be, yeah, I'm connected to a bulletin board and I'm transferring a file, I'm downloading it. You could even tell the difference between download and upload. Like all the lights on your modem would tell you that. So you can figure them out. This is exactly what we're doing with a hard drive. So I would get 2 commands, drive seek complete and drive ready, which is basically your terminal and terminal ready commands that you would have on your modem. Okay? So That's what I'm going to do. I'm going to hit. Now on the Deepsbar, the nicest thing about this is that you can turn the power on and off with the keyboard for the drive. So F11 and F12 are your power on and then your power off. F11 is power on, F12 is power off. So now your Deepsbar, if you look at the board in front of you, you will see that the Deepsbar has a top, and then there's a wire coming out of the left of the card, and that wire going out of the left of the card is an eSATA cable, and the eSATA cable is connected to your destination drive. The destination drive is where you are writing your data to. Now that drive is not to be taken apart. Do not disassemble that hard drive. That is your drive to write data to. If we have drives that are bigger than the drive that we're writing to, I have other drives and we'll be swapping them out. So these drives that we will be swapping them out with are not to be disassembled. You're only going to disassemble the surplus drives that I have in the back, which are also a variety of different sizes and brands. Okay, I've got every brand or every major brand that I can get my hands on in the last 20 years. So it's quite a bit of effort to actually get them so that you guys can destroy them. $500 worth of drives. So every class. So in this process, why is your class so expensive? Oh, we destroy $500 worth of drives every class. So in the process of doing this, you are looking at your source drive, which would be coming off the top. Now right now, none of you have a source drive. All of the source drive, everything that you're connecting to for the drive you're going to recover is off the top of the card. So those cables, there's a ribbon cable, there's a SATA cable, and there's a set of power cables. Only one of the power items needs to be plugged into anything at a time. So I'm on SATA right now on mine, and so there's a SATA split. There's a split for the old hard drives, IDE, and there's a split for new SATA drives. Everybody good so far? So only one of those should be plugged into something at a time. It should only be coming from the card when it's plugged in, not the power supply. Don't take a cable from the power supply and plug that into your source drive. You will not have control of the power of the drive. It only comes through the card. Everybody clear? I will have to correct somebody in this class in the process of doing this, so I just want to make sure I'm clear. Nothing comes from the power supply. The only cable that the power supply is plugged into is it's plugged into the Deepsbar. You'll see one on the back, on the tail of the Deepsbar. That power is to supply power to the drive that you're hitting the key. Then there is power from the power supply that goes into the destination drive. Because the Deepsbar doesn't control the destination drive's power, it just stays on all the time. Okay? So that's how that's configured. So you're dealing with everything off the top of the card. Alright, when I hit F11, it's going to supply power from the tail of the card up through that cable, and then you'll see the SATA connector, and you'll see it respond on the screen. Now, I do need to explain something about DOS and timing and things to you. Back when DOS existed, you had to actually compile every single thing for every driver for everything that you wanted to talk to. You could not, there's no Windows interface, there's no nothing doing the work for you. So you had to have everything built in yourself. And you had to choose your timing, because as you give a cycle to the screen, you are taking a cycle from something else. So this is all done basically through what would be considered Pio mode, because every transaction involves the processor and the entire system. So at this point in time, all the hardware and all your response, you're getting a response, you get a cycle from a keyboard, you get a cycle from a mouse, you get a cycle from a CD-ROM, the cycle goes on for all of your hardware. So your screen has a refresh rate. If you lower the refresh rate so that, let's say, it was refreshing every 1 millisecond, which would be super fast, then it will take all your cycles from the rest of your system. If you give it 100 milliseconds, then again, it's slower, but you don't see everything that happens because your drive is responding. How fast do you think your drive is normally responding to most commands? Well, we know what the upper limit should be in Windows, right? 600 milliseconds. So in reality, depending on the size, it's not about sectors, it's about blocks. You can do single sectors or you can do blocks. your transfer rate is going to be somewhere between 1 millisecond and 6 milliseconds. So it's super fast by comparison. So that means I've got, you know, upwards of, I don't know, if I'm setting this to 100 milliseconds, then I'm going to miss every 20th cycle or whatever else it goes through. So I'm not going to see all the screen refreshes. Does that make sense? So it is possible to have something happen that you never saw because the screen didn't refresh fast enough. So you'll see some weird things every once in a while, like there will be a flag. So as these flags go across the top, there'll be a flag sometimes right here that blinks, and there'll be an I or INX. An I or an INX. I mean, you can come in the class if it's that important to you. You don't have to be secret about it. I mean, I publish this stuff on the internet. So anyway, so you'll see a screen refresh and an eye. The best way I can describe the eye to you is a Monopoly board. As the drive spins around, there's one spot that's the beginning of a track. So there's always a signal that's the beginning of a track. Not every drive will display it, but it's called an index. It's the index for the track. So you'll see a blinking light that says INX. And when you see that, that's really good news, because that means even in situations where maybe the rest of the system did not read data, that you see a head working because it sees the beginning of a track. It may not sync correctly. It might not read the system area correctly, but that means that the head is seeing something, and you know a head is good. Does that make sense to you? So I'm using the Deepsbar to do things like if you call Deepsbar and you talk to them, oh, tell me about the index, like they'll have no idea what you're talking about. Like these are things that I've done over the years that I can tell if a drive is starting to work and getting the heads to work. And so I can see these small little things that are happening. So I'm just going to do it, and I'm going to power on my source drive, and you're going to see busy, drive seat complete, drive ready. As long as the drive is somewhat functional and the system area is working, I should get those responses. Every once in a while, you don't get drive seat complete and drive ready, and the busy goes away, and it's a screen refresh problem. And if I hit R and rescan the poll, sometimes I'll see it. So just know that that happens. It's all about timing, and I can control the timing of the screen. It's just I don't want to take away all the cycles from the recovery. Okay? All right, so F11, it powers on. So my Toshiba switches to physical mode. The 03 switched from 00 to 03, which is a physical connection. So it's not logical, it's not network. There's a couple other commands that you could do over other devices. They also had add-on boards. They have add-on boards that do USB drives, and that'll be a different type of connection. And you'll get different commands, but you still use the exact same interface. This is the coolest part about it, is even if you're doing USB through a USB board, your response and your process is still the same. It's just the commands that being sent to it are sent over USB 3, which is a slightly different protocol. So you'll get different errors or different things that happen. All right, so I did that. I got drive seat complete and drive ready. Okay, now I'm going to hit R and rescan the bus, because it is up. You just can't see it at the moment. It's all manual. So I hit R. All right, now here's the important thing. Serial number came from the platter, system area. So does your LBAs. The LBAs are sometimes a seed value, like Western Digital, back when they had 40 gig drives, had 2 terabyte as a number that would go right there. If this wasn't working and it didn't read from the system area, it may display 2 terabyte. On something that 2 terabyte never existed, like back in 2002, there was no 2 terabyte drive. So you would get ridiculous numbers. Now I know why they chose 2 terabyte. Why do you think they chose 2 terabyte as the number? It's what?
You never thought you'd get that big.
Nope. It's what?
Formatting.
Say it again?
The formatting for files.
No, but you're close. The reason GPT exists is to get past 2 terabyte. So 2 terabyte is the highest number you can count to in 32 bits. So if your system is 32 bits, then the largest partition structure that you can create is 2 terabyte.
That's why MBR was.
That's why MBR is dead, because MBR is 32 bits. And so the highest partition that you could add into the table on an MBR system is 2 terabyte. So it's 32 bits, so you know your 40 gig Western Digital would be a 32-bit drive, only because that would be the highest number possible. And so it's 4 billion something, something, something. You divide by 2 because it's 512 bytes, so you get to 2 billion 300 and something. So our limitation to partition sizes is strictly because we were on 32 bits. So that's where we ended up with, so all FAT. FAT is 32. So FAT 32, or well, we have a FAT 64 which is called exFAT, but before that there was no other option. So Windows 95 OSR2 was 32-bit, so from then on FAT was 32 bits, and it could be 2 terabytes. All the way till today, still the way it is. However, Windows, what's the largest format that you can format FAT32 on any Windows system since Windows 2000 for 20 years now? What's the largest partition structure you can make that's FAT32? Anybody know the question I'm asking? You want to format a hard drive and you want to tell it FAT32 so that you are compatible with Linux and Macs and whatever else you want to be compatible with. What is the largest you can format FAT32 on a Windows system?
4 terabytes.
2 terabytes the limit. You can't do 4 terabyte because it's 32 bits, so 2 terabytes the biggest it can be. However, what's the largest partition size? Because the point I'm making is that Microsoft limited it. Microsoft, who made FAT32, decided 4 or 5 years after they made it, 4 years after they made it, because they made FAT32 in basically 1996-ish, right at the beginning of 1996. Windows 95 was, OSR2 was like 6 or 8 months later. It was FAT32, and FAT32 could be formatted to 2 terabyte. If you had a drive that was 2 terabyte, there was no such thing. So in 1999, when they released Windows 2000, which was never supposed to exist, or XP was never supposed to exist, they chose that day that make a limitation on the size you could format a drive, because they wanted everybody from that day forward to use, because that was the very first Windows NT version that wasn't for servers or workstations. That was the end user's machine that used NTFS. That was the first release of NTFS to the public in a commercial released desktop application that was not the server or the workstation for development or things like that. You know what I'm talking about? Because we had Windows NT 351 for work groups, Windows NT server, Windows NT 4 terminal server, which basically is Citrix, or the original Citrix platform that they stole from Citrix. There's a long story there. But basically they extorted Citrix into giving them a piece of code, which you now know as RDP, which allows you to do remote desktop protocol. They stole that from Citrix because Citrix was an OS2 platform, and when OS2 died and they went to NT, then they had nowhere to go. So Microsoft had to make a deal with them, and they had to give up something. So that's how we got RDP in our systems and desktops. It was developed by Citrix originally. And then Citrix went and built a new version called Picasa or something, and they have a new interface that's faster. Windows 2000 is the first commercial release for desktops that you would have at home or on your laptop. It had the first version of NT that we would have used as a personal version. Its big thing was it was a secure file system, and that people couldn't get into it. When you would have security on your machine and say, I am Bob and I don't want Sally to touch my profile, you could have your own private files, and Sally could not log in and touch your files. So it was all user-based, and that was because of the file system being NTFS. So they drove everybody to NTFS, so they decided FAT32, the largest you could ever make it again, was 32 gigs. So if we got bigger hard drives, they could force everybody to go into NTFS. And let's get rid of FAT. They were trying to kill FAT. They didn't want FAT to live, because if you get past 32 gigs, it's inefficient. If you have a 2 terabyte drive, the cluster size is very large. And if you put a 1K file into a cluster, you lose the rest of the cluster. So you could have 1,000 small tiny files and fill a 2 terabyte drive up, but it only be a couple of K. Does that make sense? So that's why it's very inefficient. That's why you have to be careful using FTK on a fat hard drive, because it fills it up with a whole bunch of small files, and you don't have the capacity. Even though it's 2 terabyte, you're only going to use like 200 megs before it fills it up. So they tried to force everybody to do this. What do we use and what did we not have when FAT32 was decided to be 32 gigs that we have today that we need FAT4? For everything, just about. Where do you use FAT32? Where are you using FAT?
Thumb drive.
Thumb drives. We didn't have thumb drives in 1999 when they made the decision. There was no thumb drives. That was a later event that came on so that we could have compatibility and carry stuff around. So they didn't even know or think about the fact that they are limiting us from formatting something that might be a future technology that didn't exist at the time. Does that make sense? That's where we're at today. So you have to use something else to format it bigger if you want to, and that's why there's formatting tools for your solid state thumb drive to get it to 2 terabyte if you have a 2 terabyte thumb drive. I don't know anybody's got a 2 terabyte thumb drive, and there's similar things, but we do have that little SanDisk now thing that there's a 1 terabyte and a 2 terabyte. It's not a thumb drive, but it's basically a solid state drive. All right, so all of these things are important because all of these things have to do with how we're looking at our file system and how we're looking at the data that we're about to get to. So now, drive C complete, drive ready. I've now read data from the drive. I've gotten my LBA numbers. So that came from the platter. The geometry of the drive comes from the platter. But there may be a fake seed value on the board that has nothing to do with that. Okay? And our model number also comes from the system area. Now, it may also have a seed value. So let's say it says Maxtor Calypso. That is the family of the drive. That is not the model of the drive. Or if it says Maxtor NP4, that's a family of drives, not the model of the drive. This stuff that's here is read from the platter and then merged together in some way that then displays the real content, and you should be able to pick up your hard drive and look at it and say, yes, that number is correct. Yes, that is correct. Now I will tell you, if you see in the serial number or the model number characters like the pound symbol and percent and things like that, then something has happened and your head is shifted a little bit, and the data that it's reading, it's almost correct, but it's slightly off by a bit shift. And so therefore you're reading content that's being interpreted incorrectly. That means you're getting close, but you're not right. You haven't gotten your head working exactly right. Does that make sense? So if you continued on from there, when you see it, you will not read data correctly. I'm trying to make sure everybody understands that because you will see it. There'll be like some weird numbers there. You'll be all happy. It looks like you got it. But no, you did not get it until you can read the content and it matches your hard drive. Okay? Because that comes from a platter, which means your head read a platter and you got this data. Now, it doesn't mean you'll be able to read the user's area. You've only read the system area, and we're hoping that we got far enough that we can read the user's area. Most of the time you can. 99% of the time you can. There'll be that 1 or 2 times that things just don't work out. Does that make sense? So we have a pretty good major, I can complete this. So now once I've done this, and I've gotten this far, because at this point I'll be adjusting things with a screwdriver, hitting F11, F12, refresh, F11, F12, refresh, adjust, try to get the head to work. Okay? When I get this far, then the very first thing I do, I don't even hesitate. I just hit enter, and then you'll get this screen. It should be blank like this if it's never seen your hard drive again. So this is a fresh configuration. It's never seen this hard drive before. If I have previously done some work, then that previous work will show up there if the serial number matches the configuration on the destination drive. The destination drive knows what you've done. So if I image now and I turn off the machine, it will pick up where it left off. Does everybody understand what I'm saying here? So if you are the very first time you've done a rebuild and you plug it in like this, this should be what you see. You should not be seeing green dots and things like that. That should bring up a caution flag in your mind that like, hey, maybe my drive did not mount correctly, because if I saw the system area and I read the serial number, then it would have started over again fresh. Okay? So I'm on this screen, then I hit F5. And F5 brings up this box. It is always restart imaging if it's never seen anything. So they call it restart imaging. It's really a clone, but so once I hit this button, this is what I'd be looking for in my rebuild. I'd be looking for green dots. If you get green dots, then for our intents and purposes, especially for your rebuild, then you can throw your hands up and be, I won. As long as you get a green dot, then I call that a success, and we will deal with whatever problems happen afterwards. Understand? So you may get brown, you may get timeout, you may get skip, you may get all kinds of stuff, because once you take apart a drive, you don't know how well it's going to respond, but that's the point. Okay? So if you do this and you get this far, those are your keys. It's going to be F11, F12 till you get to see the serial number and the model number and the LBA blocks with the R for rescan. Once you get into the box, after you hit OK, then you are going to hit F5 and you're going to hit Enter. You are going to do that all day long until you get everything working. And then from there on, we will then start to improve our process. Okay? So, now, there's a lot going on in here. And I need to explain to you what the Deepsbar can do, so you know the tools that you have. So if you're going to be a programmer, you have to learn what your syntax is and what your possible choices are for things that you can use. Otherwise, you're going to rewrite the wheel from the beginning and the ground up. So I need to explain some of the other things to you, okay? On the screen that you're looking at, the top thing, everything that's red, is a menu, and you can access it by hitting the Alt key and the red letter. And then you will also see menu items, and when the menu items are there, then you will also see from those your other choices. So you will see Control-C does this, blah, 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 and so on and so on. Actually, in reality, this one used to be Control-S. It still is, it still works. They made F5 so you could do it with one hand, one key. So they added that later, and so sometimes I still do Control-S. So it's just a habit. So that's your other option. And then the rest of the things that can happen. So all of your menus, that's what you're doing. You're controlling things by that. Okay? Then this is your status right here. And then right about here somewhere in an imaginary line, there will be error flags. So if you have red and Christmas lights and things like that, there will be red errors. They all have a meaning. Those are actually the errors that it's returning for sectors and things that nobody else tracks, like Ncase or FTK, but every tool, including a bunch of free tools in Windows even, will tell you what the errors are. So for some reason, Ncase and FTK can't write what a free tool will give you for nothing into their $4,000 program, and they don't advance their process at all. It's straight up, I'm not kidding, a DD engine. That's all that they're doing. So anyway, so red flags. Then you'll get a status of unread. Those are ones that it tried to read and then adds a count to. And then right here in this area will be some status information for what's going on. As it's reading, it'll tell you. Every once in a while this gets cut off, and it's cut off on the projector right now by like one row. There's a line going up and down, and you'll see it again when I reset the screen. Sometimes it readjusts, and then you can see it's a DOS problem with projectors. There's a line going up and down, and the line's intention is to tell you I'm alive. So basically there'll be a line that's kind of like my processor utilization line. It's like, oh yes, I'm alive, I'm alive, I'm alive. So that if nothing else looks like it's going on and the screen's not refreshing, you can tell that something's still going on, okay? B means block. I am reading content in a block. A block is anything bigger than one sector. If I switch to a single sector reading it, it'll say S. So I'll get S for sector, a B for block. An R is a reset. There's two types of resets. One is a hard reset, which basically powers down, waits so many seconds, and then powers back up. And there's a soft reset, which is like a blip. It's just basically power off, power on. And so the little one, the little R, is the soft reset, and the big R is a hard reset. So these are some of the control mechanisms